Okay, maybe other people will join later. And I don't understand why few people only are attending this year, but I understand, you know, the situation is different with respect to usual, and also I understand that you have many commitments anyway, and so I know that some of you decided just to attend fully remotely, meaning that by reading my web pages, looking at the video, maybe that you can manage anyway. Okay, and then I think we can start by looking at the exercise. Let me share my screen. So it's here. So this is something that doesn't, yeah, here it is. Just 1 second. I wait for you to see my screen. Okay, here it is. So as you may remember, last time we started the exercise with RStudio, and the exercise it is, as you may remember, an application of the CERC formula. I think I still have here the test of the exercise, which you can download from my website. I just want to remind you that there is this graph here, which is in a way useful, and we will see later how to use this sketch in order to develop our exercise. It is extremely important, you know, it is extremely important to understand what the data file that you collect from individual observatories, what are the kind of data that they give to you. Typically, as you know, we need data on sea depth at the breaker line. Also, we need data on wave height at the breaker line for a given time period or a given return period. And then we need data on wave orientation with respect to the coastline. And this sketch shows that the angle that we get in our data file, the approaching angle of the wave, is alpha. It's the wave between the it's the angle between the wave direction, the red arrow that you can see here, and the vertical direction upward. So alpha, as you can see in this figure, is the angle that we get in our data file. Actually, as we will see later, we need to compute the along-shore sediment transport. We need the angle between the wave direction and the coastline. So what we need is alpha 2 in this case, and therefore, as I said, it is extremely important when you get data on wave direction, wave behavior. It is important that you understand what the numbers represent, because depending on what the numbers represent, you have to write your algorithm in a consequent way. And you know, it's usually they use a quite standard format, but it is extremely important when you look at the data also to look at the headings, at the description of the data. It is important that you look at the metadata. The metadata are information accompanying the data, which give to you an idea of what the data are, give to you specifications on the data. Now, let me then go back to the website, and you know, this code that we have to write is an application of the CERC formula. And first of all, let me show you where is the theory explained, because the theory was explained in coastal engineering in a dedicated web page, and the web page is here. I put the address on the chat now. Give me 1 second to get here the chat. I'm putting the web address on the chat. Here it is. So you can click there to get this page here, which gives to you again the theory. We will just show to you the theory later. We will just go through the theory later in order to get back some concepts. And now I'm going to the end of the page. Give me just 1 second here to get to the proper section. The proper section is here. But what is important is to look at the concept here of the model that we have to apply. So what we need is to apply a very simple model. The very simple model should describe what in this figure is called delta xi. And let me just open the image in another graphic program so I can manipulate it a little bit to show you what I mean. Just 1 second. New image here. Okay, I have the painter. Let me see if I can just write here. Yeah, it's visible. Perfect. Okay, now let me expand it and let me do this. Okay, very good. So this is what we need to work on. So the CERC formula is giving to me an indication of the value of Q in, which you can see here, Q in, and it's giving to me an indication of Q out. We have to compute Q in and Q out for any delta y. Delta y is here, it's a spatial time step. And look, this simulation is done by applying the CERC formula to each spatial step, delta y. And also we have time steps. So we need a simulation that runs over spatial steps at each time step and then runs through the different time steps. So it's a two-cycle simulation. At each time step, for a sequence of time steps, we have to run the simulation along each spatial step. And by computing Q in and Q out, and by computing the difference between them, the difference Q out minus Q in, we get an estimate of the value of this yellow volume, which now I am trying to circle with the red line, the red pencil. So this is the difference between Q in and Q out, give us an estimate of this yellow volume. And what are Q in and Q out? They are volumetric sediment rates. So their difference is again a volumetric sediment rate. What does this mean? It's a volume of sediment per unit time. So in order to get an estimate of the yellow volume, which is the volume of sediments that is accumulated in each spatial step at each time step, we need to multiply the difference Q out minus Q in times delta T. So what we have to compute is, let me see if I can write on the graphic, on the graphic table. What we have to compute is Q out minus Q min, and this is to be multiplied times delta T. Okay, and this gives us precisely this yellow volume. Okay, and then this yellow volume can be approximated to like a parallelogram, And if we divide this yellow volume times delta y here, and times the C depth at the breaker line, which is an approximation of this, okay, then we get an estimate. Volume divided by delta y divided by C depth gives us an estimate of delta xi. Delta xi is the movement of the beach, the movement of the coastline. So basically it gives an idea of whether the coastline moves forward or backward. If it moves forward, it's deposition. If it moves backward, is erosion. Deposition is also called accretion because it's an accretion of the beach. So this is very simple because, as you see, it's a difference between two results from the CELC formula, which is divided by the geometric feature of this yellow volume to get the missing geometric feature, which is delta xi. So it's very simple. But on the other hand, the algorithm needs quite a thoughtful approach because it is important to pay attention to the signs. When you compute a difference, it's a difference between two quantities. What does this mean if the difference is positive? Does this mean that there is accretion or there is erosion? It depends on the sign of delta xi. So we have to pay attention to the signs here to always consider what given sign means. Negative is accretion or is erosion. Positive is accretion or is erosion. And also we have to consider the sign of the trigonometric functions that we compute, depending on the convention that we adopt for the angle. So depending on what is depicted here, just 1 minute here, depending on how alpha is measured, of course, the trigonometric function sin or cos changes its sign, and therefore it is extremely important to pay attention to what the data represent, what is the sign of the trigonometric functions that we compute. So what does the sign of the estimated sediment transport means, and what the sign of delta xi means. This is my premise. And then we can start building the code. We can start building the code by keeping in mind all of these considerations. And this is why the code is not simple. It's not simple because, you know, if we make a mistake, it's probably a mistake on the sign, or it's a mistake because we exchanged a sin by a cos. And therefore, it is extremely important. One thing is to pay attention, and another thing is let's make some tests. When you build a code, it is extremely important that very quickly you make rapid checks of whether what you are building is consistent. In this case, it's particularly delicate because there are many things to pay attention to. So we have two options here, either to start from scratch, building the code, or using a pre-prepared code. And what I did actually is to propose to you a pre-prepared code. And the reason why I prefer this solution is that, you know, for clarity of presentation and to minimize the time that we dedicate to this problem during our frontal lecture. This is why I prefer to give you a pre-prepared code. On the other hand, when you use codes that are already prepared, I'm sure that I already mentioned this kind of precaution of attention that you have to adopt. When you use a code that is already prepared, you have to make sure that everything is correct. And in order to do that, you have to make sure that you understand what the code does. If you get a pre-prepared code and you blindly apply it, you blindly run it, this is, in my opinion, extremely risky. And for a professional engineer, it's something that you cannot tolerate. Because, okay, in some cases, you can take the risk. If the code is well tested, if it's a widely used commercial code like Excel, okay, you can take the risk. But when you use codes that are not extensively and massively tested, it's extremely important that you understand what the code does. It's extremely important that you understand the theory behind it, because this is essential in order to detect possible errors, mistakes. Okay, so now what we have to do is to look at the website, at my web page of the course. I'm getting it. Give me 1 second. And sorry, I can't find it. I need to get oriented. Here it is. Okay. And let's open. We already downloaded the data, so I assume that you already downloaded and you have available the PDF describing the exercise. I assume that you have already available the geometry of the shoreline. I just opened this data file in order to refresh our minds to see how they look. So this is the geometry of the shoreline. It gives the X and Y coordinates of subsequent shoreline points. So it gives the geometry of the shoreline by points, by giving X and Y coordinates with an arbitrary orientation of the X and Y. Usually Y is north and X is east, but you have to check this. Usually when you get coordinates of points, they may be geographical coordinates, so they may be given in terms of latitude and longitude, and then you may need to translate them if you want to get them in a local coordinate system. Let's assume that we have a local coordinate system here, which is already given. And I listen a micro that is open. Do you have any question? Okay, if not, please close the micro. Otherwise, it's something. Let me see. I don't understand. Okay, anyway, it's not a problem for me. I see that your micros are turned off, so I don't think it's a problem by you. Okay, and just 1 second. Let me do like this. Okay. Okay, so as I said, these are the coordinates of the coastline. Let me go back and refresh our minds with the wave forcing. The wave forcing, it's given in terms of the spatial time step. It's 150 meters. It is the delta y that we adopt. So again, spatial time step. And sorry, it's the delta x that we adopt. And then there is the time step in seconds, and then there is 1000. 1000 is the number of the time step of our simulation. So given that the time step is 2 minutes, we run the simulation for 2000 minutes. So something like less than 1 hour. And then we have this data. We already got a description of what these data mean. And let's now refresh our mind by looking at the code. We are not using all of this information. This is typically the information that you get from a wave forcing file. We will use only some of them. Okay, good. Now let's open the example R file. When I click on it in my PC, I already get it. I already get the opportunity to open it with RStudio. I'm not sure you are getting the same opportunity. Let's suppose that you don't get it, but I guess that you have, if you have RStudio installed, you get it. But we already discussed this, so let's open it with RStudio. And Now here we are. Let me clean my working environment. We have the console here, and let me see. Console, okay. Just 1 second. Okay. So I need to put. I want to get the environment here displayed. Just 1 second. Okay. And okay, let's start in this way because I think it is simpler, but let me just make a check. Okay, here it is. Sorry, I couldn't find my environment. I wanted to check that I don't have any environment is empty, so in my case, so this is fine. And as you remember, here we have the script and here the console. So let's look at the script and let's repeat what we have done quickly. These are some preliminary data entries to define the sediment mass density, and this is a typical value that we can adopt in practical application, 2600 kilograms per cubic meters. It's the sediment mass gravity, if you wish. No, it's density, sorry. And then we have the seawater mass density. It's 1025 kilograms per cubic meters. And then there is gravity acceleration, porosity of the sediments, and K is a dimensionless parameter which is used to compute the actual sediment transport. We will have a look at the CERC formula later. There is a K parameter which is an empirical parameter that we need to adopt. And also there is the slope of the beach, and it is not used because the CERC formula doesn't use it. But if you use other formulas for computing the sediment transport, you may need to use this. And then there is the D50, it's the beach grain diameter. And again, this is not used here, but it is given because, as I said, there are other formulas besides CERC for computing the longshore sediment transport that use also D50. So if we want to run these instructions in the console, I have to select them. I can select them with the mouse, or I can select them with the keyboard. Now I am using the mouse. If I want to use the keyboard, I use the arrows. I go at the beginning of the line that I want to run. I select all the lines that I want to run, and then I have two options. Either I can click on Run. If you look in the upper part of the console, you see where the black rectangle appeared. You see that there is a description: run the current lines or selection. And this is a possibility. You can click on Run, or you can press Ctrl plus Enter. And you see that in the console, everything went forward. If you expand the console, you see that we obtained the result that the instructions are copied from the script to the console and are executed. This is precisely what we wanted. And you see that it's extremely efficient to work in this way, to work in RStudio in this way. Okay, now we have instructions to scan the data. And let's first of all scan the coastline geometry. So there is first there is an initialization of t equals 0. This is used later, but let's define it. And okay, and then let's scan the file coast txt. I scanned it. Okay, it doesn't exist because I forgot to set my working directory. So I set it. You see what I am doing. I choose my desktop. Oops, I was too quick. I choose my desktop here, open, and now I try to run the instruction again. So again, Ctrl plus Enter, and now you see that it went on. It scanned the file, and then there is the opportunity here to, not the opportunity, there are the instructions here to divide the two columns in the file. You remember that the file had two columns, one with the dy and one with the dx. And here I can do this. I put the two columns in an array which contains the dx and the y. Very good. Now we have to scan, sorry, not the coordinates. This is an array with the coordinates, x and y coordinates of the coastline. PR1 is the array with the x and y coordinates of the coastline. I'm keeping the chat in front of me. If you have any question or you can't follow me, let me see. Okay. Just 1 second. Okay, good. I'm putting the chat in front of me. Just 1 second. I need to put it in the other screen. Otherwise, you don't see what is displayed here. Good. Perfect. So if you have any question, let me know. So we scanned the coastline geometry. Now let's scan the file wave forcing. I am scanning line by line. So you see that in the first extraction, I am putting the argument here n equal 1, which means that it reads only one number. And this is my dy of the simulation. Okay, this is the spatial step of my simulation. And then there is my dt. It's the dt is the time step. And then there is the number of the simulation, and delta t. Very good. I am just selecting one line each time and pressing Ctrl plus Enter. One thing, you see that when I scanned dy, I just put the argument n equal 1. When I scanned dt, besides n equal 1, I put another argument, skip equal 1, because I want to skip the first line. Why do I want to skip it? Because I already read it. I already read the y, so I don't need to read it. I need to skip that line where the y is reported, and then later on, in the third reading instructions, I have to skip 2 lines. And then in the other instruction, I have to skip 3 lines. Okay, so we got, now so far we uploaded n delta t. Let me check if it is okay, perfect. And then let me upload PR2. Wave forcing, and the PR2 is an array with five columns, so let's declare here that it is indeed an array with 5 columns. Very good. Okay, now we have to start working on this data. We have to start managing it, and the first thing that I want to do is to put in a vector which I called XLC the position of the coastline, which is the first column of my coastline file. Okay, good. Now, in the second column, what is given there? Again, the second column of the coastline file. So what is given there? So pay attention, because I now realize that a few minutes ago I gave to you wrong information. The second column, I didn't remember. It is not the y coordinate. Actually, what I get in the geometry of the coastline file is 2 columns of x coordinates, and the y is just given at regular time step of 150 meters. So I don't need to give the y, because the y is already known. The delta y, it's uploaded in the second file, it's 150. The second column of the geometry file, it's the limiting position of the coastline. In some elaborations, in some simulations, you may need to put a limiting position to your coastline. For instance, you may put a limit to the erosion or a limit to the accretion, and a limit to the erosion may be given by a seawall, for instance, and a limit to the accretion may be given by other infrastructures like a breakwater. So when there are limits to the evolution of the coastline, you have to take them into account. Actually, in this exercise, we are not taking them into account, but still, I wanted to show you that there might be a limiting position, and this is given by this vector XLCL. So XLC is position of coastline, XLCL is limiting position of the coastline. So let's upload it. Okay. Now there is now the 5 column of the wave forcing. The first column, you remember that we uploaded the wave forcing in an array which we called PR2. So now let's give to the first column of the array, let's assign it to a vector DLF, which gives the position of the breaker line. As I said, we will not use all of these variables, but I want to upload all of them. Now, HB is the wave height at the breaker line. This is needed. LF is wave length at the breaker line. This is not needed. DB is sea bottom depth at the breaker line. This is needed in CRC. And then we have alpha, which is wave angle with respect to y, upward y. And here you see a specification. Let's read it. Positive when waves are oriented towards, increasing wise, which means upward wise. Very good. Instead, if you get the wave oriented towards decreasing wise, y coordinates, then the angle would be negative. In this case, in our case, the angle is always positive. So let me see your question, Camille. And I don't. A red dot appeared next to HB when I uploaded it. I don't. Okay, a red dot in the script. You mean in the script file? So somewhere here. Okay. I don't understand why. Did you get let me see. I'm just waiting for your figure. Just 1 second. Okay. And please have a look at the console. Do you see any error on the console? Okay, so I don't have an answer. I should be able to reproduce it, but actually, let me see. No, I don't get it. It is really strange. I don't know why. And let me see if I click. So I can get it by clicking with the mouse. You see that? And I'm not sure what it means. Let's forget about it. So just turn it off, and then later on, if we have some time, we can understand what it means. Okay? I think it may be an interesting option. So it is nice. It would be nice to inspect what is the meaning. As you know, I'm not a massive user of RStudio. So there are many things that I don't know, as well as there are many things that I don't know with R, of course, because it's a program that is very, very extended in terms of opportunities, in terms of tools. And if you discover anything, it would be very interesting if you posted your discoveries in the chat. So one nice thing, Camilla, would be if you tried to make an attempt during the next few days to try to understand what the red dot means. And usually when I need help with some software, I search on Google, as you know. So I would look in Google for red dot RStudio R script. So I would search for red dot RStudio script and see if you can get any help from there, or there is the help of RStudio, but usually it is much easier if you look on Google. It's faster. And if you discover anything related to opportunities, or you have some nice scripts that you elaborated, for instance, for drawing nice plots, it would be very nice if you shared them. It would be indeed useful to me, and above all, it would be useful to you. Okay, it shows up if you click next to the line number. Yeah, this is true. In fact, this is how I can get it. I'm sorry that you don't see my mouse, but I am just clicking on the left of the number. Okay, now I think we got... let me just make sure that I run these instructions. Keep in mind that if you run the instructions twice, it's not a problem, unless of course you have to look at the content of the instruction, unless it goes to modify iteratively something. But in this case, it's just data uploading. So anytime we repeat the instruction, we just overwrite what we did before. Now, here we are computing the y coordinate. And the y coordinate, given that we know the delta y only, we need to integrate the delta y to compute the y's. And integration is given by the function cumsum, cumsum, which means cumulative sum. And what is cumulatively summing this instruction? It is cumulatively summing a vector which contains 20 repetitions of delta y. So if I execute this instruction, I get a vector, and you may look at the console how it looks. Let me expand the console a little bit and clean it. If you now press Y, you get the cumulative sum of the delta y's, which is what we wanted. So it is a quick, rapid check that what we did is fine. Good. Now there is an instruction, read the comment, to keep into memory the original position of the coastline. And we do this because XLC will be iteratively modified during our simulation. So let's keep into memory the initial value of XLC. Good. Now here there is a plot, and before making the plot, let's expand the plot window, otherwise we get a mistake, we get an error. And the plot is showing the lines of coastline and limiting coastline. So it is built by y coordinates, and this is y. You see the black line that is shifted a little bit because it is built, the black line and the red line, they are built for the same y's and different x. You get an error because, did you try to expand the plot window as I did? Because look, if I keep the plot window too short, then if I now run again, you see that I get an error, me too. But if I expand the plot window, okay, very good, I expand the plot window and I get it. Again, I want to draw your attention on the fact that this plot is, the independent variable is y, so it's not x. Of course, you could draw it in a different way, but the way it is drawn here is by giving the y's, which are the same for both lines, and the x are different. Okay, so this is why you get a shift of the black line towards the right. Okay, very good. So this is the red line is the limiting position. Now we are ready to start our computation. Let me just first of all, let's create a vector QL, a repetition of zeros, and we will see what is the meaning of this vector. Just to clarify what I want to do, I would like now to move forward 5 minutes and then I'll take a short break, okay, a 5 minutes break, and then another hour, probably another hour to discuss again this exercise, and then 15 minutes break. Okay, so let's start with the simulation. As I said at the beginning, only Camilla was attending at that time. As I said, we need to run the simulation at each time step, and at each time step we have to run the simulation at each spatial step. So we need two cycles, one cycle over the time steps and another cycle over the spatial steps. So let's start with first of all, let's start with a preliminary cycle. The preliminary cycle is meant to compute average coordinate of the coastline. Let's look at what I am highlighting here. There is a cycle over 19 time steps. Remember that the coastline is given by 20 points for which we have y and x. Now, we want to substitute each x coordinate of the coastline with the average between two subsequent coordinates. Why I am doing this? Because I am smoothing the coastline. Smoothing, which means that I want to eliminate singularities, which may be given by uncertainty in the data or may be given by sudden changes of the coastline orientation, which are very local. I don't want to take into account the very local geometry, because sediment transport, it depends on the macroscopic behavior of the beach. I don't have to look at the very specific behavior in a given 150 meters time spatial step. I need to look at the shape of the coastline over a larger spatial scale. So by substituting each coastline position with the average between two subsequent points, I am now referring to a spatial scale of 300 meters. And even if I am still working on the same number of spatial steps, and therefore the difference between coordinates is always 150 meters, but still I am substituting each point with the average between two neighbors, and therefore I am in a way smoothing it. I am enlarging, broadening my perspective. And you may ask me, why just two spatial steps? You could take the average of 3 of them. Yes, this is true. I just worked with 2 because I know that I have to avoid local singularities. I think that if I take the average between 2 is just enough. But it may happen that you run your simulation and the model becomes unstable, which means that probably you need to widen your perspective even more. So it is something to carefully evaluate. So let's compute this average, this smoothed version of the coastline. And one thing, let's try to add on this plot that I have in the right now the smoothed coastline to see what it changed. I don't have here in the script such an instruction, so I need to take it from the previous one where I drew the red line in the graph, and let me copy it, and be careful not to copy the return carriage character. So don't copy the full line like here, copy until the end of the instruction, and then let's paste it in the console, and let's modify it. Let's write lines, not XLCL, but rather XLC, the new XLC, and then the color, let's put it in blue to distinguish it. And you will see that you will obtain a smoothed version of the black line. Let's see what happens. You see, it's smoothed, and you can understand that it's smoothed. If you look on the left, you see that there were singularities, there were spikes, which I smoothed out. So this is the purpose of this smoothing, namely to avoid singularities. Okay, perfect. Now let's reduce the size of the graph because I need space to look at my code. Okay, so we already did this. Now let's start with the simulation, and I suggest that we take a 5 minutes break. Okay, so take breath a little bit, and then we will see each other in 5 minutes. I just drink some water and I am back to you. Just 1 second that I need to pause my screen record. Okay, so here I am. Now we are ready to start our simulation, and I am putting the related script in the top of our script window. And as I said, the simulation is articulated over 2 subsequent cycles. The first one is over, oops, sorry, I need to change the screen. The first one is over the time steps. You see the comment, there is written cycle along the time steps. And it's a 4th cycle. It's between 1 and n delta t. So look at the syntax of the 4 instruction. I think we discussed it already last fall, but it's important that you refresh your mind and remember. Okay, so let's execute it. Okay, good. And then we have to go with the other 4 cycle along the spatial steps, along the shoreline. And if you look at the 4 variable, it's double I. So the first 4 was over the I variable. I am highlighting it, I. The second 4 is over II, okay? And just because we need to keep them separated. So let's enter this second 4 cycle. Very good. And then we have the computation. First of all, there is here an auxiliary variable that is created at each spatial step. It's the delta x, is the difference between 2 subsequent x. You see here, it's XLC I double I plus 1 minus XLC double I minus 1. So it's the difference between, for each x is the difference between the 2 neighbors. So double I plus 1 minus double I minus 1. And this difference, it's important for us to compute the angle between the wave direction and the coastline. Okay, so what I am doing is, let me see if I can, in the graphic, window. No, this is not the graphic window. Just 1 second. Let me see if in the graphic window I can write it. Let me try to, because I got a graphic blackboard, and but I am waiting for another one because this one is a temporary solution. I'm not very good in drawing here. But let's see if I have a coastline here. I'm sorry. Here it is. If I have a coastline here and I have a given wave direction here, the angle that I have now, it's this angle. This is the y direction. Now I have my alpha, it's this one, okay? What I need to compute is what I called alpha 2, which is this one, okay? And in order to compute this angle, what I'm doing, if I am referring to this x coordinate here, let me change the color of my pencil. If I am referring to this coordinate here, okay, what I am now doing is to, 1 second, to refer to the two neighboring coordinates here, and then I am computing the difference in x. So if I draw the verticals to the x-axis, this is my x, I am now computing this difference. Okay, and it's the difference between, if this is my coordinate double I, this is double I plus 1, and this is double I minus 1. Perfect. And it is a similar figure with respect to what we got in the PDF. Let me show you. You see here, it's more or less similar, and the difference which I am computing is the delta x that you see in the horizontal direction, and again my purpose is to compute alpha 2. Now keep in mind that alpha 2 is equal to alpha minus alpha 1, and alpha 1 can be computed once I know my delta x and my delta y, because with a simple trigonometric function I can compute alpha 1. So basically, if I go back to my graphic representation, once that I know this coordinate here, and once that I know this one, which is my delta y, so this is delta y, this is delta x, I can compute this angle here, which is alpha 1, which is the same angle here. And therefore, by computing alpha minus alpha 1, which is again this one, alpha minus alpha 1 gives to me precisely alpha 2. I hope it's clear. So this is why I am okay, this is why I go back to my code. This is why I'm computing this difference between two neighboring coordinates. And look, even in this case, I refer to a quite large portion of the coastline. It's a large portion which is comprised between 3 subsequent points. And again, the wheel is that of referring to an average geometric feature of the coastline. Now there is here the computation of alpha 2, which is equal to alpha minus alpha 1, and alpha 1 is given by the inverse tan of XLC divided by 2dy, 2dy because I considered 2 spatial steps. And if you look back to my graphic window, you can easily understand that alpha 1 here, just one second, alpha 1 here is equal to arctan of delta, arctan of delta x divided by delta y, which is precisely because you know that delta y here is equal to, or let's say delta x is equal to delta y times tan alpha 1, and therefore you can easily demonstrate this computation here. Okay, and then this is the computation of alpha 2, which is the angle between, again, wave direction and the coastline. Perfect. Now I am computing. I need the wave height. Why do I need the wave height? To compute the energy of the wave at the breaker line, and therefore I need the wave height at the breaker line, and to compute subsequently the volumetric sediment transport rate. So this is my auxiliary variable, which is the average between the 3 subsequent wave heights at the breaker line that refer to my considered data point. And you see that it's an average, it's the sum of 3 wave heights divided by 3. Okay, good. Now, here there is a test instruction, which we are not considering, and it's a test that I put there in order to check the value I wanted to put a fixed value of alpha 2 in order to check whether the sediment transport rate, once it is computed, takes a meaningful value. And therefore I wanted to try with several different values of alpha 2 fixed by me, not given by the geometry. So this test instruction allows you to make some checks. Once you write a code from scratch, it is useful that you refer to very simple cases in order to check whether or not in these simple cases you get the expected result. I hope everything is clear. Okay, now I am computing the energy of the wave, and let me go to the web page where the theory is presented. So let me go there. The theory is presented here. Okay, let me go up and let's look at the wave energy. So wave energy, it's this one. For instance, this is a possibility. So it's square wave height times rho g divided by 8. So let me go back to the script, and you see that it is precisely what is written here. And then there is a subsequent computation. I think we need, I think we need to execute these instructions. Very good. Now, there is a subsequent instruction here, which is, I go back to the web page with theory. It is the computation of the total energy density of the wave at the breaker line per unit horizontal area. It is what we just computed here, okay? And then there is, sorry, because I don't remember, okay, the computation of EBW, which is the wave energy flux through a vertical plane of unit width perpendicular to wave propagation direction. So this computation here is shown here. And let me execute it. Okay. And then there is finally the application of the CERC formula. And here you have the parameter K. And the formula is just what is presented in the web page. I go back to the web page now. It's presented here. This is the formula which I am applying, or let's say I am applying this. Okay. Or maybe that it's the subsequent one. I think I am applying this one actually. Okay, which is derived by the previous one with simple transformations of trigonometric functions. And also I am including the parameter K, which is included here. Okay. So this is what I need to execute, and then we can close the curly bracket. Very good. Just 1 second, I take a note. I take a note because there is one thing that I noticed that I want to clarify in the code. It's nothing important. Okay. So here there is a consideration on the sign, and it explains that if QL is positive, let's read it, and it's positive is if alpha 2 is lower than pi half. In this case, it means that the sediment transport is from right to left in this given exercise. Okay, and so QL positive in each spatial step means that the sediment transport is from right to left in our exercise, according to the conventions, according to how we represented the wave angle, and according to the given geometry of the coastline and the given wave direction. Okay, very good. Now let's move forward. And then I think there is a curly bracket. No, okay, it's closed later. And then there is the computation of the difference between the sediment transport in each spatial step. I need the difference because, as I said, in order to get the yellow volume, as I said at the beginning, I need the difference. And when you compute the difference, which refers to 19 points, we have to be careful because the difference between 19 numbers is given by 18 numbers. So you have one less element in the vector, and this is what is written here on the right. Be careful, the resulting vector you cannot read here, but if I move, is counting one less element with respect to QL because I am taking the differences. Okay, let's take the difference. And then here it's I have two test instructions. If you want to print on the screen something, you have to use the function cut, as it's written here. Now they are commented, so no need to compute them. Remember, I am still inside the time cycle. Now what I am computing is the sequence of the dxi, the sequence of beach moves forward or backward at each time step. Okay, and I put a negative sign here because I need to ensure coherence. If alpha 2 is less than pi half, the sediment rate is positive. Therefore, a negative increment means that there is deposition and therefore accretion of the beach. So if you move in this exercise along the coastline from the left to the right, a negative increment means that there is deposition. If you have a decrease in sediment transport, it means that there is deposition in the considered spatial step. You know, to understand how these signs are used and manipulated is the real problem of this exercise. This exercise is very simple. If you just look at the computation, if you look at the code, it's a very stupid one. The only thing that requires attention is, as I said at the beginning, is the signs. Okay? Perfect. Now we computed the X, and now we can compute the new position of the coastline by summing to the old position the X. Okay, at each spatial step. So let me close the 4 cycle in space, and then I can close the 4th cycle in time. Now there is an error because I think I forgot to some instructions, and the way we have to remove this error is to execute the code again from the beginning of the 4th cycle, because you know probably I forgot something. I forgot a curly bracket. Let me start from scratch, and it's here from scratch, and let me select all the instructions and see whether I can successfully run the code now. And up to here, let's forget about the last instruction, which is a plot instruction. Let's forget about it. Now Control Enter, I am executing everything, and now it's fine. Now the last instruction, it's a plot of the new position of the coastline. Let me expand the plot window. The problem is that in the plot window now I have a blue line which I put by my initiative. I need to remove it. So let's redraw the plot with only the black and red line. So I go back to get the plot instructions. The plot instructions are here, so let me select them, execute them, and then you see that I removed the blue line. I got a new plot, and then I can go at the end of the code and plot with a blue line the new position of the coastline, which is this one. Actually, I was expecting something a bit different, but no, it's fine. I think it is fine. So you see the new position. It's a new position that is a bit peaky. And what does this mean? It means that there is some instability here. And if we run the program with more than 1,000 time step, we would get a configuration that is a bit too peaky. And this means, as I said, that there is some instability. Let me just run the code, the whole code from the beginning, from scratch, because I want to see whether it is confirmed. No, you know, it is now a little bit better. It is changed because I think there was a mistake in the previous run that I did. Still, you see that the coastline it's a bit peaky, but I mean this is acceptable. The previous one, which there was a mistake because you know, I executed the code again and probably I forgot to reset some vectors. Now you see that if I execute the code again and again, I get always the same result. I think I forgot to reset some vectors. And look, the blue line, the new coastline, is missing the two extreme coordinates, and this is because I needed to compute differences in sediment transport, and therefore I am missing the two extreme coordinates. And again, let's make some consideration on the new shape of the coastline. It is a bit peaky, not too much really, But still, if I run my simulation maybe for 2000, 3000, you would see that you get a configuration that is a bit may become unstable. Unstable means not regular, up and downs and so forth. What we are expecting from the shape of the coastline under a wave forcing is something that is smoothed out. It's not very peaky. I mean, the new coastline cannot be. And therefore, if we end up with a configuration that is too peaky, it means that we need to make the algorithm more stable. More stable means, as I said before, referring to an average coastline so that I don't have many changes in the geometry from one spatial step to the other one. Or another solution may be that my steps are too large. Maybe that I have to reduce the length of the time step, because instability may also be given by a numerical approximation, and numerical approximation is reduced if you reduce the size of your spatial and temporal steps. So this is something that you have to carefully evaluate. I tell you that when I got these data, which are real world data, and in terms of wave forcing, the coastline was it's hypothetical, but in terms of wave forcing, I took real world data, and I had to make several attempts before coming to a version of this exercise that was ending up with a quite stable simulation. I think it is a nice training, it is a nice example, this exercise, which gives to you an idea of how these algorithms work. Actually, there are commercial softwares which do the same thing, which are more accurate because they have checks for instability, and also they may use several sediment transport formulations, because one reason here for instability may be that the CERC formula is not reliable in estimating the long-short sediment transport, and therefore, you know, it may be very useful to compare different formulas. These are empirical formulas at the end of the story, so it may be very useful to compare several of them in order to get a more comprehensive picture. But still, I think that if you start by making this exercise, it's a very good training that allows you to understand how the concept works. So I think it is indeed useful. What I recommend to you is to make an attempt to fully understand how the code works. I'm sorry. And if you have any suggestion for me to improve the code, to make the code more stable, just let me know. This is something, the code is something that I got from the web. It was written in a different language, and I got it from the web, but actually it was done by one of my Italian colleagues. I think it is a good code, but I also made some changes. So, I mean, if you have some ideas for refining it, I would appreciate that. Okay, so the next question that you may ask me is maybe, is this relevant to Harbour engineering? And my answer is definitely yes, and I will give you an example later, maybe today, maybe next week, where beach morphodynamic is extremely relevant to Harbour engineering. In a few words, I can tell you that when you build an harbour, when you design an harbour, you have to estimate what is the effect of the harbour on the shoreline morphology. It is extremely important because harbours have an impact on the morphology of the shoreline, and therefore may have an impact on tourism, on fisheries, on whatever. And it's extremely important when you design an harbor also to study how the coastline will evolve around the harbor itself. I think that with the exercise I am done. Do you have any question so far? Because for the next couple of hours I will turn to coastline protection infrastructures and something that you in part already know, and then I am changing I am changing the topic. Sorry. And so if you have any question, take this opportunity. Question or suggestion would be fine, while I am closing the windows that I don't need anymore. Okay, thank you, Gabriele. Just 1 second. So you can see my face and I can sorry, Camille. The instructions were clear. Okay, thank you. Thank you very much. I thought it is good to know. Okay. Okay, so before making the next break, I think let me take the opportunity to introduce the next topic. Okay, so let me close RStudio. Okay, good. And also I don't need this one. Good. Okay, so let me share the screen. Okay, here we are. So the next lecture is beach protection strategies and structures. And as I said, this is something that you, to some extent, you already know. I just wanted to give to you my overview in order to connect with the next lecture, which is design of groins. You've already focused on the design of breakwater. According to the agreement I have with Professor Archetti, you didn't focus on groins, and this will be my next lecture. But before moving to that, I want to give you an overview. And it's a descriptive lecture, and I just, as I said, this is a personal overview. First of all, I think it's a personal overview, and I want to give it to you because I think it's important that you get an overall perspective according to my viewpoint of what are the measures that you may adopt if you are called to design a strategy for managing a shoreline. And these strategies are needed when you build infrastructures like harbors, because these, as I anticipated, have an effect on the morphology of the coastline. And I want to give you an example before making the break. And the example is linked somewhere down here. Let me find the link. The link is let me see. Let me see, bypass. Okay, here is the link. It's down in the web page. I want to just to have a look with you at this link. Let me just copy the address. You may also, I put it on the chat, you may want also to have a look in your PC locally. Okay, this is the link. And if I click on that, it's a project that was done in Australia, and it is called the Tweed River Bypassing Project, the Tweed River Sand Bypassing Project. And let me give you an overview of this project. This project was needed because there is not specifically an harbor, but there is a river getting into the sea. It's an important river, and let me have a look if I will remember. I think it's general information. I need a map, and it's not here. Just 1 second. It's send delivery, I would say. So if I click on operations send delivery, there should be the map. No, yeah, here is the map. So let me expand the map. Okay, what you can see here, I clicked on operations and send delivery in the website. So here you see this is a coastline in Australia, as I said. You see that there is a river which is entering into the sea, and what happens when a river gets into the sea and you have a long shore sediment transport. Basically here the sediment transport comes from the bottom right of the picture and goes upwards in the picture along the coastline. What happens is that a bar is formed in correspondence of the river entrance with no intervention, no human intervention. You get a bar in front of the river entrance, which is caused by the longshore coastline. And then the presence of the bar, it's a problem for navigation. This is an important river with boats going back and forth. You can see also from this aerial picture that there are boats flowing there. So the idea when you want to protect the delta of a river, the estuary of a river, is to build vertical walls that go into the ocean, and they stop the longshore sediment transport. In this way, the longshore sediment transport is in part diverted offshore. If you look at the color of the sea offshore, you can see a kind of a clearer stream offshore, which indicates what is the trajectory of the sand after building these walls. And by stopping the longshore sediment transport, these walls avoid the formation of the bar. So it is a solution that is frequently adopted, but the problem is that in doing that, you originate accretion of the beach. Accretion of the beach, in this case, in the bottom part of the figure, and you can clearly see that the beach in the bottom part before the walls goes into the ocean more with respect to the upper part of the beach, where after the walls, where you don't have any more supply of sediment delivery. And the result of this intervention was that they got an accretion of the beach in the lower part of the figure, and in the remaining part of the beach they had an erosion. They had an erosion which they tried to stop to mitigate by building the groin that you see in the upper left part of the picture, the Kira Point groin. Note that groin can be spelled with the Y or the I, depending on the use of American or US English. American or UK English. And here it's spelled with the Y. That groin, it was displaced in order to stop erosion, because the groin again stops the longshore sediment transport, and therefore it gives rise to accretion of the beach before the groin and erosion after the groin. So you see clearly the difference in the beach shape before and after the groin. So they tried to mitigate beach erosion on the right of the groin by building the groin, but still they had the problem that the beach was progressively eroding, and this is a place where people like to surf a lot, and they had an impact on the tourism, a social impact which they needed to solve. So what was the solution that they devised? It's a sand bypass. So they get the sand, if you look on in the bottom left of the picture, let me see if I can, yeah, I can copy the image. That's great. Let me open it into my graphic program so I can manipulate it, because otherwise it's really a stress for me and for you as well to follow on a figure with my word only. I need to, just a second, it takes some time, I don't understand why, to upload it. Maybe it's a huge figure. Okay, here we are. So, 1 second, very good. So, as I said, there is sediment transport, a longshore sediment transport that is, I need another color, just 1 second, because otherwise I need another color and another dimension of my paint. And let me take the red. Good, now it should work. So the longshore sediment transport is going in this direction. Let me take, I need to increase again the dimension. Okay, let me see. So this direction. Okay, now it's okay. And you can see that there is a kind of, here, you see that this is the new trajectory of the sand. But you have erosion here, erosion here, erosion here, everywhere, because of the reduction of the sediment delivery. And this is why they put the groin there. Okay? Okay, good. So what they decided to do is this bypass. So let me change the color of my... So they take the sand from here. And this is a sequence of sand pumps. You see the red, the black dots are pumps. What they do is they inject water on the seabed. They take the water from this blue, from the Tweed River, from this blue line. Here there is the intake. And then they pump water from the Tweed River. They inject water into the seabed, because in order to move the sand, and then they, with pumps, they pump the sand into this pipe, this direction, and then the sand gets into this red pipe across the river, and there is a first delivery here, and then there is a second delivery here, and then other deliveries, precisely, let me move the figure, another delivery here, another delivery here, and maybe even here, not always, but sorry, doesn't write. Okay, and here. I hope it is clear. And I mean, this is an example where an infrastructure like these river walls created a problem that needed to be resolved with a massive project, and it was successful. It is a very interesting project because they monitor the volume of sand that they can pump, and they indeed pump a lot of sand. And the project was studied by applying a beach morphology model. Of course, it was a complicated model. You see that here there is a complex circulation of currents and waves and also the shape, the geometry of the coastline is characterized by singularities, and therefore they needed to make a careful evaluation, a careful assessment, but still it was indeed very, very successful, the project, and was and it is a very good example of how beach morphology, how beach geomorphology interacts with human activities and the design of facilities. Just take into account that here they have an harbor, and it's a boat harbor, and the boats also need to, to have the access to the harbor that is free of any obstacle like bars, and so all of these activities are connected to managing this harbor and navigating into the river. Okay, good. I think I can now go back. We don't need to refer to this anymore, and we can go at the beginning of our lecture, but now we make a 15 minutes break. Okay, and if you have any question, please take this opportunity. Otherwise, let's take 15 minutes to get a coffee. So let me stop the recording. Okay, good. So I need to share the screen. Okay, so let's discuss about beach protection strategies and structures. And first of all, let's talk about classification of beach protection measures. Just one second, I go down in the web page. I just want to see if I have here. Just one second. Okay, no, perfect. Okay, so let's talk about classification. As I said, classification is useful in order to help us remembering what we are talking about and fixing in mind. First of all, we can identify 4 categories of interventions for the preservation and maintenance of beaches. And these 4 categories are manage the retreat, first of all, and basically it doesn't contrast any change that is occurring in the shoreline, but rather managed retreat identifies a new line of defense. So you go back inland in order to contrast soil beach erosion by simply moving back. And this is sometimes adopted, especially for sites where there is no touristic interest, or we may intervene, and interventions may be classified according to 3 categories, and there are interventions to hold the line, the shoreline, such as seawalls. There are interventions to move the shoreline forward in the seaward direction, and these are, for instance, beach replenishments or any intervention that stimulates accretion of the beach. And then there are indirect measures, like, for instance, green engineering methods. Basically, instead of using infrastructures, they favor the development of conditions which stimulate beach accretion, and this favoring of the development of these conditions must be obtained without using hard infrastructures, and then we call them indirect measures. As I already mentioned, they also can be called green engineering methods or soft engineering methods. These methods are today very popular because, for obvious reasons, because in light of the emerging concerns about sustainability, these measures, of course, which make use of natural materials and stimulate the growing of vegetation, stimulate recreating a natural environment. These are today preferred. Of course, there is not a unique recipe. We discussed four categories of interventions. If we exclude managed retreat, which it's a particular case, the other three categories, there is not really a unique recipe. And very often the ideal solution is a mix of methods. And the way they are mixed should be devised by looking at the peculiar behavior of our case study and also looking at the stakeholders' opinion. Beaches are an extremely relevant, from a societal point of view, are an extremely relevant resource, and therefore their management nowadays is decided and designed by involving stakeholders in the discussion. When you involve stakeholders, you will get a group of people who are in favor of hard infrastructures, other groups of people who will be in favor of green engineering. It depends on their interest and their attitude to safeguard common and public goods. And as I said, there is no unique recipe, and it's when we talk about environmental protection and sustainability, we don't have to be dogmatic in a way that it doesn't exist a solution that applies everywhere. It's a complex interaction between humans, between society and environment, and has to be managed by looking for the best solution of this integrated system. So there is on the one hand the will, which is well motivated, I think, to stimulate the development of society and therefore to protect commercial activities, to protect tourism. On the other hand, there is the will to protect the natural environment for reasons that are well known, and also because the natural environment is instrumental to developing the societal activity. So it's an integrated system. There is a two-way interaction. The environment has an influence on society, society has an influence on the environment. And this complex interaction is to be, first of all, understood. And then, basing on our understanding and depending on the peculiar behavior of the case we are studying, we have to devise what is the best solution, which usually, as I said, it's an integration of methods. And of course, for the engineer, there is a preliminary knowledge to gain. This preliminary knowledge is based on our understanding of the functioning of beach morphology on the one end and the functioning of our intervention on the other end. And there is also an economic evaluation that has to be done. We have to very often to carry out a cost-benefit analysis. And also keep in mind that there is an evaluation and assessment that has to be done of the local laws in force. As for harbors, we need to pay attention to what are the laws and the recommendations at the local level and the international level. So again, it's an interdisciplinary effort which we have to carry out with a modern and innovative vision. How to gain this innovative vision is very often a challenging question, but let me say that there are some fundamental requirements which are openness. We have to be open and to share information, openness and willingness to adopt a vision that has to be multifaceted. So a vision that has to encompass an understanding of the local economy, of the local local and global economy, and local and global societal development. And but I mean, the basic requirement is to be open and willing to listen to people, listen to different opinions with an approach that has to be supportive, cooperative and positive. It may seem something trivial, but actually it's not. I mean, usually in decision making, people like a top-down approach. And the reason why they like the top-down approach is that the bottom-up approach, consultation, discussion, takes time and a lot of energy. And also people require a special attitude to be able to manage other people. And I think these attitudes should be also gained by engineers. You are an engineer, you will be an engineer, you will be involved in designs that will require interaction with people. Take into account and try to develop your capability to be open, and your capability to listen to other opinions and adapt your own opinion basing on what you listen from others. It's becoming a fundamental requirement today, even in the university, to be a professor. And I really realize that more than ever we need to be able to work together. Okay. Now, let's talk about, before I talk about active measures, let's clarify another classification. So interventions to hold the line and to move the shoreline forward are also called direct measures for shore defense. Direct because they involve a direct intervention of humans by building infrastructures, by especially building infrastructures actually. And they include infrastructures that are located in the beach area, and these are also called hard engineering methods. So when you talk about direct measures, measures involving infrastructures, they are also called hard engineering methods. And they include active measures which modify the local hydrodynamic behavior and therefore sediment transport, and passive measures that protect the coast from erosion without modifying the hydrodynamic circulation. Okay, let's talk about active measures. Again, they modify the hydrodynamic behaviors and therefore modify the sediment transport. And they are our primary interest. They are breakwater, groins, and beach nourishment, and also sand bypass, which we discussed before. Passive measures, on the other hand, include seawalls and revetments. We will see what revetments are, and berm protections. Okay, very good. So our aim is to discuss in detail what groins are. You already know what breakwaters are, so I'm not discussing breakwaters. You already know all what you need to know. I will discuss groins. I think I will also discuss beach nourishment. Maybe I need to check how much time is left after we move forward. We are on schedule now, but I need to, given that this year I introduced some new topics, I need to check how much time is left when we finish to discuss groins. We already discussed a little bit of sand bypass. I'm not going to discuss it anymore. I want, just before we discuss the groins, to discuss with you seawalls and revetments, just in order to clarify what they are. So revetments, they are also called, revetments are protections of the beach, and also the term is used for meaning protections on river banks. Revetments are reinforcing measures of the beach and river banks to protect them against erosion. They can be made by stones, like you see in this figure. If you see in this figure, you have a seawall just on the right of the sidewalk, and at the base of the seawall, you have rock revetments to protect the foundation of the seawall. And these are also called rip-rap revetments. When you have a revetment that is made by stones, we also call it or stones, or let's say other loose material like material from demolition or tetrapods. You can substitute the stones with material from demolishment of buildings or with tetrapods. And in this case, we talk about rip-rap revetments. The revetment may be also made by concrete, and in this case we just say revetment by concrete. And I just wanted to discuss it. If you click on the link here, it's interesting. I think it is an interesting link, and it's something that I'm not explicitly including because it's very descriptive. But I think I am clicking now. I think it is interesting because there is a nice, if I well remember, there is a nice, yeah, it is here, a nice table which talks about seawall types. I think it is very instructive. It recently appeared, and it explains what kind of seawall you may build. And we can distinguish between vertical seawalls, and there is first an illustration that explains where they are particularly suggested, in which conditions. And then there are advantages and disadvantages. And there are examples with figures. So you can click on the figure here, and this is a vertical seawall. So it's I think it's really a nice table. And then there are other types of seawalls, carved seawalls. They are often used because it's the concave structure helps to dissipate the energy of waves. If the seawall is vertical, the impact between the waves and the seawall is a shocking impact. And so they can be, if you look at the disadvantages of vertical seawalls, there might be expensive damage in a short period of time. And then if you use a convex structure, it helps to dissipate the energy, as I said. And it's nice to see this figure here. You clearly recognize what is the purpose of this convex shape. It's to attenuate, to distribute the impact of the wave along a convex surface, which helps in reflecting the waves back by avoiding a shocking impact with the vertical wall. And as I said, I think it is a nice example. And then there are seawalls made by mounts, and here it's an example of what we mean by mounts. And it's like a seawall. It's not vertical, but it's like a seawall if the mounts are displaced in this way. The shape is close to vertical, and they have advantages and disadvantages, and they are porous, and therefore they help to dissipate the energy of the waves. But on the other hand, they are made by loose material, and therefore they may suffer from damage. But the appearance is more environmentally friendly. Okay, good. And also there is a description of natural barriers, but I think in this link what is interesting in this is precisely this table. Okay, I'm not discussing the design of seawalls. There are standard procedures for determining what is the forcing of waves against seawalls. Basically, you take the energy of the wave and you convert this energy into an action. because when there is the impact between the wave and the seawall, you get a conversion, a transformation of the energy flux of the wave into a forcing against the seawall. And there are suggested procedures to compute this forcing. Also, you have to be careful about erosion at the bottom of the seawall, and we have to prevent, of course, erosion. And but I'm not discussing these computations, which are, relatively easy to learn. There are empirical formulations and the physically based formulation that you can easily learn by yourself, and I think also Professor Archetti may have said something. But basically the moral of the story is that I'm not discussing the design of seawalls. And also berm protections are something a little bit different from seawalls, and the idea here is, I hope you remember what is the definition of the berm. The berm is the upper part, is placed at the upper part of the Schwarz zone. It's the limit, the upper limit that is reached by waves, and therefore there is, at this upper limit, there is a deposition of sand, and so a kind of elevated zone is formed, which is called the berm. The berm is extremely important because it's a barrier. It's a barrier against erosion, and we have to avoid that the berm is eroded, because otherwise, if it's eroded, you have a sudden increase of erosion over the beach, and one way is to protect it. It may be protected by revetments that are placed with sub-horizontal, almost horizontal placement, and revetment in the form of gravel, they may be, or tetrapods. So these berm protections are another, if you want, more environmentally friendly way of building a barrier against erosion of the beach. We will talk a little bit about berm protections later. Okay, now let's focus on infrastructures, and let me refer, I would like to propose to you a scheme of direct measures that can be used. I think this scheme is useful to understand what are the possible solutions. And the seawalls is something that we already discussed and we already know. When you look at this figure, please look at the legend first. So the legend and the way the various type of structures are represented. The emerging structure with this crossing pattern, the submerged structure with the dashed line, also the protected break between structures, and sometimes when we place a sequence of structures, we need to protect the breaks, because in the breaks you have a concentration of the energy of the waves, which is in a way conveyed by the structures into the breaks for diffraction, etc. And therefore, given that you have a concentration of energy there, you need to protect them. Or sometimes, let's say, it's advisable to protect them. And also look at how emerging signals are presented here. The emerging signal is needed sometimes for when you place submerged structures, and signals are maybe needed to when there is navigation in the interested zone, and in order to alert on the presence of the submerged structure, which may be dangerous for boats, even small boats. So the seawall is self-explaining. Here you see an example of breakwater with protected breaks. You know what breakwaters are. I just wanted to show that in this case, in this case the brakes are protected also to safeguard the durability of the breakwater, because of course if there is a concentrated erosion in the brakes, then you have a damage that may impact the breakwater. And for this reason, you see that even the extreme ends of this sequence of structures are protected. And if in this case you see a combination of groins with breakwater. So what is the main difference between breakwaters and groins? Groins are effective in limiting the along-shore sediment transport. Breakwaters are effective in limiting the cross-shore sediment transport. So depending on the dominant process, you may need one rather than the other, or a combination of the two. Keep in mind that the along-shore sediment transport usually is effective in the long term. It's a long-term process. The cross-shore sediment transport is typically a short-term process. The cross-shore is particularly relevant during storms. The long-shore sediment transport is something that is relevant in the long period. So depending on the dominant sea behaviors, you may need, as I said, groins rather than breakwaters, or a combination of the two. And I think this figure it's effective in showing a first combination. So submerged breakwaters with signals and protected brakes in the combination with groins. Here, keep in mind that when you combine different structures, you have to carefully consider also the visual impact. Not only the impact in terms of beach dynamics and hydrodynamics and morphodynamics. You have also to consider, depending on of course, on the behaviors of the considered site, you have to consider also the visual impact. And many infrastructure cause, of course, an increase of the visual impact. And you have to carefully consider this, because there is today an increasing concern against the visual impact, the artificialization of the land and the sea. So people don't want to artificialize more than needed. When you combine different structures, usually the impact in terms of visual appearance, artificialization, I cannot pronounce it well, but I hope you understood, it's a considerable impact. And this is why in some cases submerged structures are preferred. The effect of a submerged structure with respect to an emerging one, I think you already know what is the difference in terms of effect. So, of course, the emerging structure is more effective, especially with regard to storms. On the other hand, the submerged structure is much more environmentally friendly. So, as I said, this is a first combination. You have an example here of perpendicular groins. Remember that groins favor the accretion of the beach on the part that is exposed to currents. I can't remember there is a term, but I can't remember it. I will remember later. But the part from which the current comes from accretes. There is accretion there. And there is erosion down, let's say, downstream the current or waves. And therefore, this is the reason why sometimes you need to put the groins in sequence, because otherwise you are simply moving the problem to the direction of the currents and waves, along the direction of current and waves. And so if you have a long extension that needs to be protected, you need a sequence of groins. the T-shaped groins are more effective. It's clear. On the other hand, their visual impact is increased. Another solution is small islands, and small islands, they have a limited visual impact. Of course, their effectiveness is more limited with respect to continuous breakwater. Now let's talk about beach replenishment. Beach replenishment, it's frequently used, especially today. It consists in bringing new sand to the beach, and of course, in doing that, you in a way compensate the lack of sediments from the rivers. And usually beach erosion, with respect to a kind of pre situation, pre something like pre urbanization, beach erosion is increased because delivery of sand from rivers is decreased for many reasons. The reasons may be that with river training we try to limit river sediment transport. Another reason may be that we dredge the sand from the river. So there is a deficit of sand supply from the rivers. And of course, if we artificially bring some sand to the beach, we compensate for this. So replenishment may be effective by itself without any structures, without any structure that is integrated with the replenishment. And this is the first case. On the other hand, of course, if you protect the replenishment, the effectiveness of the intervention is increased. You can protect the replenishment by using groins or submerged breakwater, which are called here protecting bar, because it's usually we identify with the term submerged breakwater a structure that is weakly submerged, like 0.5 meters, with respect to average sea conditions. When we talk about submerged bar, the submergence is higher. You see here 1.5, 2 meters, and the bar is, of course, an artificial bar. It's another form of protection because the bar frequently induces the breaking of waves. If you bring seaward the breaking of waves, the impact of the energy and the forcing of broken waves on the beach is mitigated. And the submerged bar is an interesting intervention because its impact in terms of visual appearance is close to zero, and its effectiveness it's very often significant. On the other hand, if you have people bathing there, of course, this is an artificial structure, and we have to be careful on the impact on tourism, not just for the risk of people, but just because, of course, there is basically a protecting bar very often implies that people cannot swim offshore besides beyond the artificial bar. So this is something that has to be considered, because beyond the bar you have an increase of the sea depth, and therefore, an increase of the risk to which people are exposed. So this is something that has to be considered, of course. Here you see replenishment protected with weakly submerged breakwater signals and partially submerged groins, so different combinations. And here there is an example of replenishment protected with groins, and then a replenishment protected with T-groins. We will see in detail why the T-groins protect the beach more effectively with respect to the normal, let's call them in this way, normal groins. Okay, and let's also say that something that emphasizes what I already anticipated. The interventions with hard infrastructures were preferred in the past, mainly because it was when the problem emerged, there were less opportunities for alternatives. When the problem emerged, the problem of beach erosion, and typically it emerged after the Second World War in many West regions. Because after the Second World War, there was the massive economic development, what is called the economic boom in the 60s, and then tourism increased in several seas in the Western world. Tourism increased a lot, so this led to urbanization of the coastal areas and increased the value of the coastal areas. And on the other hand, river training was extended, and dredging of sand from the rivers and in some cases from the beaches was also increased because of the need to build new buildings, new roads, etc. And so beach erosion became an issue around 1970, 1980, and at that time the green solutions were still poorly known, and the hard infrastructure were accessible with a relatively limited cost, and also they looked effective in terms of durability and in terms of efficiency of the solution. You know, when people invented the concrete, the reinforced concrete, they thought it was like about 150 years ago, they thought that the durability was unlimited. They realized later that the durability of the reinforced concrete was not unlimited. And the same happened for several hard infrastructures. People got the feeling that this hard infrastructure had an unlimited duration. Like a dam, people thought that the durability of a dam was unlimited, like the durability of bridges, because they thought that, the materials were much more durable with respect to what they actually are. And therefore, they had the feeling that barriers made by concrete and breakwaters had a higher effectiveness and a higher durability, and they didn't consider alternative solutions based on green engineering, soft engineering methods. Also, there is one thing to say that if you build a hard infrastructure, it looks like something that is very effective to people. Instead, if you plant vegetation there, it's less appealing. If people are concerned by something, by a threat, a risk, they tend to like more the hard solution, because the hard solution you can really see there. This is clear to me when I deal with, for instance, with water resources management. If you build a dam, you see a huge dam, a huge lake, you see a lot of water. So this is very convincing as a solution. If you talk about limiting the leakage, people are not so convinced because they don't see the leakage. And the same here. If you build a breakwater, if you build a groin, people can see it. It looks like something very huge, very strong. If you plant vegetation there, which may get to the same final result, it's less convincing because it's not strong. It's not, okay, it's nice to see, but it looks like you adopted that solution because you were forced by the green parties to use it, not because we believe in it. And so there is a huge communication effort that has to be done. And again, you have to gain the capability to listen from people and to convince them. So hard infrastructure were preferred at the beginning, but then in the 80s of the last century, the green politics emerged. And I suggest you to read this article here. It's a Wikipedia article that speaks about the green politics, because the green politics had a considerable influence on engineering practice and modern way we design environmental management, and the green politics, like any school of thought, has its downsides and its positive aspects. It was no doubt on that very positive. On the other hand, there are downsides, because indeed in some cases the green solutions are less effective than hard infrastructures. And therefore, as I said, very often we need a combination. And also the green politics was a bit, I think, a downside, but this is a personal opinion, so feel free to disagree. A downside of the green politics is that it's often prescriptive and doesn't easily lend itself to compromise. It's, I mean, a prescriptive way of thinking. And therefore you need a particular effort to reach a compromise, to reach an agreement between fans of the green politics and fans of hard infrastructure. Is not easy because, I mean, these people tend to fight among them rather than looking for a compromise. And it is, I mean, it is an aspect of democracy. Democracy is, of course, it gives the right to the people, to everybody, but on the other hand, concertation and reaching a compromise sometimes in democracy is not easy. Absolutely, we need it, because there is no doubt that in order to design environmental management for the best, we need a democratic approach. There is no doubt on that. Nobody questions this. On the other hand, the democratic approach requires an innovative effort of stakeholders, engineers, to listen to others. This is what I already discussed before. Okay, and so I think I already discussed this. Peculiarities and limitation of breakwaters and groins, and let me see if there is something that I forgot. I'm taking a look. I think okay, beach nourishment, I think I already described it. And here there are some details that I invite you to read. So how also beach nourishment could be coupled with infrastructures that are made by natural material, like geotextiles, sandbags, and sometimes they are an interesting solution. Like sandbags, they are interesting because the bag is done by by organic material. I was still thinking to democracy. Organic material, and the organic material, as soon as you place it, it looks like indeed a bag. It's not really good looking, but with time it degrades and takes an aspect that is close to natural. So this is indeed interesting to build infrastructure with natural material, and the natural material with the help of innovative material like geotextiles and material that looks natural, even if it's reinforced. So I mean, there is ample room for creativity here, and the creativity is essential when you talk about environmental protection and minimizing the visual appearance. Creativity is indeed very important. Okay. And then here there is some consideration on seawalls and berm protection. So please read it. Here there is nothing, it's very descriptive, there is nothing conceptual. And a final discussion on direct measures, which again I invite you to read. Okay, this is my introduction, and then we can move to groins design. I would like now to make a 5 minutes break, and then we go on up to 1:35. Give me this time frame if you agree. If you have some limitation to go to up to 1:35, let me know. Okay, so if you agree, we can take another break. Okay, very good. So I'm stopping the screen recorder. Okay, here I am. Everything should work fine. Okay, let me check the... Okay, the chat is fine. Okay, so good. Let's go back to the previous screen, and let's click on design of groins then. It's a bit slow, just give it the time to open. Let me click again. Okay, here we are. So first of all, groins may also be open. So what you see here in this picture, it's another example of a groin. It's open. Groins are not only made by rubble mounts, they can also be made by wood, and can have different shape, and they can be impermeable, or can be, we say that they are a synonym of open groin is a permeable groin, which means that they allow for some water to pass by, and therefore also some sand to pass by. But even if they are permeable, they are a barrier against a long-shore sediment transport. And here there are other examples. They are widely used to protect beaches. Again, they should be used when there is significant along-shore sediment transport. In this solution here, which refers to the Liguria region in Italy, they used a shape of the groins that it's conceived to create beach pockets, and also you see that they are built in a way that minimizes or makes more gentle the visual appearance. They are made by use rubble mounts, and the shape is especially conceived in order to look as natural as possible. Of course, it may look funny if you try to to shape a beach in a way that looks natural, and if you look at the inland direction, you see a lot of buildings that are not natural at all. So, as I said, there must be a well-conceived mix of shaping of the human intervention, seaward and landward. So, first of all, let's say that groins can be classified as either long or short, depending on how far across the surf zone they extend. So, the surf zone is the zone where people typically surf, and it's extended from the breaker line of the waves up to the Schwarz zone, and groins that traverse the entire surf zone are considered long, whereas those that extend only part of way across the surf zone are considered short. And in order to clarify better what I mean for surf zone. Let me go back just 1 second at let me open another window here, not this one, sorry. Okay, let me go here and let me go back in here to our tutorials. I just want to open a figure which I think it is not really here. It's in beach morphodynamics. Give me 1 second. Okay, beach hydrodynamics and morphodynamics. It's here. Okay, very good. So you understand here what is the surf zone. It extends from the breaker line, around the breaker line basically, up to the level inland where you get still a significant sea depth, and then when you get close to the beach you have the Schwarz zone where typically waves go up and back and forth up to the beach. Okay, so again, if groins completely cross the surf zone, then they are long. So if they get up to the farthest breaker line, they are long, but they may be also shorter, and then they are called short groins. Of course, these are relative terms because the surf zone, the extension of the surf zone changes depending on the season, but we refer to average condition. And sometimes we get groins that go well beyond the breaker line, and therefore they are typically long. Like instead, groins like these ones, which you can see here in Cogoleto in Liguria, they are short ones. Groins can also be classified as either high or low, depending on how high is their crest. And of course, the high groin is more effective, especially with respect to storm. The low groins are effective in normal condition, and when a storm comes, then they may be less effective. So depending on the functioning that we expect from them, we have to select the right type. And also they can be directed perpendicular to the shoreline, or they can be placed at an angle with the shoreline. It depends on the dominant wave direction. Usually, if waves are coming from a given direction, it's better to give an inclination to the groins so that the waves they are directed towards the dominant wave direction, so that the waves arrive parallel to the groin in a way. And so let's say that about the design. We already spoke, first of all, about permeable or impermeable groins, and that's okay. And let's talk about the design. First of all, groin design is described extensively in the literature. I make reference to material that is public domain, as usual, and it's basically carried out by using empirical relationship. And the reason is the usual one. We are talking about very complex processes, very complex interaction, time-varying interaction between the beach and between the beach morphology and the beach hydrodynamics. It's not possible to describe this interaction in detail, and therefore we make reference to empirical formulas or empirical rules which are derived from experience. In case a detailed assessment is needed, in case we feel that there is too much uncertainty related to the use of empirical formulas with respect to our design project, then we need to make lab experiments with small-scale models. It's very common to make experiments on small-scale models when we have to make coastal engineering design and harbor design. It's anyway interesting to know the rules of thumb, empirical rules that drive the design of groins. And so let's discuss about these. And about this, there are several of them, several empirical formulas. I focus on the most important ones, which, however, give us an idea. And they don't give us a final, an indication for the final design, what we also call the executive design. These empirical formulas, as usual, can be used for the preliminary design. And then for the final design, we need either to make lab experiments or to make a more refined assessment by considering several different potential solutions and carefully analyzing what are the pros and cons of each of them. So what are the parameters? What are the parameters determining the response of the shoreline to groins? First of all, we have parameters related to wave behaviors, which determine the along-shore sediment transport. Of course, we need to gain quantitative knowledge of it, and therefore before turning to groin design, we need to assume that we have quantified the wave forcing and the main behavior of along-shore sediment transport. So this is something that we already know. We know how to do it. There is a statistical analysis implied. And so let's assume that we already know everything about this, and let's discuss on the response of the groins to this considered forcing. Keep in mind the exercise that we just did, because this is, I think, an excellent input to understand the concept. So we understood what are the characteristics of along-shore sediment transport. We understood what are the dominant parameters, wave height, wave angle, and we understood how the along-shore sediment transport models the coastline, models the beach. Actually, what models it is the difference in along-shore sediment transport as we move along the coastline, where we have a positive difference, meaning that the sediment transport is increasing. It means that there is erosion. Where there is a negative difference, sediment transport decreasing, there is accretion. Now, we talked about limits to the coastline, and groins are precisely a kind of those limits. If we put in the model we just developed a barrier perpendicular to the shoreline, it means that when we reach that barrier, the sediment transport goes to zero. So the sediment transport is stopped, and you have an accretion before reaching the barrier, because the sediment transport needs to go to zero. And then when you pass the barrier, you get a sudden increase of the sediment transport, and sudden increase means erosion. And the experience we just had with the model tells us how we can refine our analysis. Besides the rules of thumb, which we are going to discuss now, it's clear that the beach morphodynamics gives us a way to refine our analysis. And by keeping in mind what we just did, you can understand the concept. And if you put there permeable groins, then you don't stop all the sediment transport. If permeability is 0.5, and permeability can be defined as the surface open, the side open area of the groin divided by the overall side area of the groin, so opens divided by total area projected on a vertical plane. This is permeability. If permeability is 0.5, it means that 50% of the area of the groin is open, and it means that you can assume as a first approximation that only half of the long-shore sediment transport is stopped. So by including in our model these constraints, we can get a refined assessment of the beach evolution after putting there the groins. So let's review what are the parameters, what are the behaviors of the groins that determine their response to a long-shore sediment transport. They are described here. Okay, so length of the groin. This is clear because if a groin is very long, you avoid bypassing of the sand, of the sediment transport. Remember the Tweed River. They put the walls well into the sea. They look like groins. And remember the sand transport, how it looked after the intervention. There was still some bypassing there. So the longer the groin, the more reduced the bypassing is. And so in some cases you want to allow some bypass in order not to give too many problems downdrift. Okay, downdrift, this is the term which I didn't remember before. So if you make a long groin, you give some more erosion downdrift. If you shorten the groin, of course the effect is more gradual. And then the spacing between the groins, it's very effective because, of course, if you put groins at a long distance, then you allow for some spontaneous beach development between them. If you decrease their space, then the effect of each groin joins the downstream or is mitigated by the downstream effect of the neighboring groin. So if you induce erosion downstream, but if the next groin is close enough, then erosion is mitigated. Elevation, we already talked about it because it determines the effectiveness with respect to what kind of waves we are considering. Porosity, it's different from permeability. Permeability, of course, is how I defined it before. Porosity is whether or not the groin is able to absorb or just reflect part of the energy of the waves. Porosity normally is much more reduced with respect to permeability. If you build a rubble mound groin, you still have some permeability there. Some porosity there. There is no permeability because there are no apertures in a rubble mound groin, but still there is some porosity. And then tapering is also important. Angle to the shoreline, and as I said before, they can be perpendicular or can be placed at an angle. And then there is shape. For instance, the T-shape is important. And then their effect depends on parameters related to beach and sediments. So the depth at the tip of the groin. The tip is the seaward end of the groin. And the depth, the sea depth at the tip is important because it determines whether bypass may take place or not. The beach morphology, the slope of the beach, the berm height, it's also effective. The depth at the average breaker line or beach closure is also extremely important. The sediment availability, the grain size and variability, the sediment density. And then we already discussed about parameters related to waves. Okay, so growing design, and there is a rule of thumb that is used to determine what is the effect of the groin. And this rule of thumb is, I think it is extremely important. And it's this so-called lambda rule of thumb, lambda shoreline rule of thumb. It was originally termed the 1/3 rule. We will understand later why it was termed in this way. So let's suppose that we have a pre-project coastline. Look at this figure, and which is the thick black line. And let's suppose that we place a groin there, and we place a groin. Here there are two groins with different shape. Let's indicate with the blue lines the high water shoreline and the low water shoreline. And high and low may depend on the tide, for instance. And now, what is the dictate of the lambda shoreline rule of thumb? It says, the rule, I am highlighting the text, that the post-project coastline during mean low water level is located between about lambda equal 1/3 and lambda equal 2/3 of the distance between adjacent groins measured behind the structure. So the distance here is G. Look at the figure. The distance is G. Okay? So if the distance, I mean between the groins, okay? And then let's call with lambda G the distance between the head of the groin, the tip of the groin, and the low water shoreline. So basically you get the low water shoreline after the project between lambda 1/3 and 2/3. So lambda G is, if you look at the figure, more or less 1/3 of G. And therefore this is the displacement of your low water shoreline. So you bring the shoreline forward up in the direction, of course, of the tip of the groin, and in a way that lambda G becomes equal to more or less 1/3, like it is shown here. It's more or less 1/3, 1/3, 2/3 of G, where G is the space between groins. So you understand what is the effect of the T-shaped groin. The effect is to reduce G. And also keep in mind that by reducing G, if you measure lambda G from the end of the T of the groin, you get an expanded accretion in the vicinity of the groin itself, because you are measuring lambda G not from the tip of the groin, but from the end of the T. And therefore you bring the shoreline towards the groin. And this is something that you can see in the figure that I showed before, which I'm going to show you. And of course, lambda g is not rectilinear, so the dashed blue lines put in evidence that you have updrift the groin, you have some more deposition, some more accretion, because the sediment is stopped, the sediment delivery, and the downdrift, you have some more erosion. So this is an indication of how it may evolve. Soon after the groin, you are expected to get a beach pocket and some erosion of the beach, and then as you get distant, as you get some distance from the groin, you have that the low water shoreline stabilizes to the continuous blue line. Now, if you look at, I go up and I want to show you the figure that I showed you before of Cogoleto in Liguria. I think you can easily recognize it, the 1/3 rule. If you look at the distance between the groins at the center of the figure, and you look at the position of the shoreline, you see clearly it's about 1/3. Between 1/3, 2/3 in the center, and you can easily recognize the formation of the pocket. The pocket is given by erosion downdrift and accretion updrift. Here, if they didn't put the T's, if the effect that they would have obtained would be that the beach would move landward. If they increase the spacing, if they increase the width of the aperture, they would increase they would move the beach, as I said, landward. They would move the beach back. So I think this figure is really interesting to understand this rule. And in turn, I'm moving down, I go back to the figure of the rule. In turn, this rule, I think it is giving a very interesting, very useful preliminary idea of how the beach would behave if after the building of the groins. I am concluding by going back to the figure of Cogoleto here. And I am expecting that here, basically, waves, dominant waves, are coming from the right to the left. And this is because these groins are the orientation. They are basically looking towards the right of the figure, the right of the picture. So this is why I am expecting that waves are coming from the right, the dominant wave. It's also interesting to notice that this is a particular shape. It's not a T. It looks like a T. It's similar, but actually it's a particular shape that was conceived in order to, I guess, in order to create these nice looking pockets. And the shorter part of the groin, the shorter protuberance, was created for limiting the erosion downdrift. I think it is an interesting idea. Okay. Now, I think we can stop here. I give to you some time to ask any question. I think I can share my screen so you can see my face. Do you think I was clear enough? And I just want to make a check and to stimulate your criticism. Thank you. I guess you are too kind with me, but anyway, that's okay. I appreciate it. Okay, students, let's meet again next Tuesday, and then let's meet again next Tuesday, same time. And then if you have any question, please write on the chat. I also put on the chat an invitation if you would like to join. I organized a meeting with all the students of the department on Thursday. It's in the chat. It's nothing technical. It's just an exchange of views, an exchange of cheers, and an opportunity to discuss our future, and in a positive way, I mean. Perfect. So thank you very much. So see you on Thursday if you are attending that, but you don't need to, of course. And otherwise, see you next Tuesday. Very good. Ciao. Ciao, everybody, and thank you.